Welcome back. This is where IP addressing gets genuinely elegant. In Lesson 21, we're tackling CIDR and Supernetting, two ideas that exist to solve a pair of very real crises the early internet ran into: wasted address space and routing tables growing faster than routers could handle. By the end of this lesson, you'll see how combining subnets actually keeps the whole internet sane. So here's the path we'll walk together. First, we'll go deep on CIDR itself, what classless interdomain routing really means, and why it replaced the old class-based system. Then, we'll build on that with supernetting, where multiple subnets get folded into a single prefix. From there, route summarization shows how that same trick keeps routing tables manageable. And finally, we'll see how routers actually pick a path using longest prefix match. Before we can appreciate CIDR, we need to understand the two crises it was born to solve. Back in the early 90s, the classful system was burning through IPv4 at an alarming rate. Imagine a company needing just 300 addresses, but being forced to grab a Class B block of over 65,000 because Class C's 254 was too small. That's 65,000 addresses wasted per company at internet scale. At the same time, routing tables were exploding. Every network meant another entry in BGP, and core routers were literally running out of memory to hold them all. CIDR, introduced in 1993, fixed both problems with one elegant move: drop the rigid classes entirely, use a prefix length to allocate exactly what's needed, and combine adjacent blocks into supernets to keep routing tables small. So let's unpack the notation itself. When you see 10.20.30.0/22, that /22 simply means the first 22 bits identify the network, written in binary. That's 3 full octets of ones plus 6 more, giving you the mask 255.255 to 2.2.0. The remaining 10 bits are for hosts, which works out to 1024 addresses, 1022 usable once you subtract the network and broadcast. Now here's the catch that trips people up. 10.20.30.0/22 doesn't actually start at 30. It covers 10.20.28.0 through 10.20.31.255. Because char 22 groups 24 blocks together, and the alignment begins at 28, not wherever you happen to write the address. And that alignment rule is exactly what makes supernetting possible. It's subnetting run in reverse. Look at the third octet of these 4 adjacent 24s in binary: 11.100, 11.101, 11.110, 11.111. The first 3 bits, 1 or 1, are identical across all 4, and that's the secret. Those shared bits, added to the 19 bits already common in the earlier octets, give you 22 bits of common prefix. Collapse them, and 4 separate routes become one clean advertisement: 10.20.28.0.22, covering 1024 addresses in a single line of the routing table. Now let's formalize that into a repeatable recipe. The same 4 steps will work every time. First, confirm your subnets are truly contiguous. 28, 29, 30, 31 are adjacent and will summarize cleanly, but skip one and the math falls apart. Second, convert each network address to binary, because decimal hides the bit boundaries where the magic actually happens. Third, count the bits that are identical across every subnet. Left to right, that count is your new prefix length. And fourth, write the supernet by taking the lowest of the original networks and appending that common prefix. Master these 4 moves, and every summarization problem becomes mechanical. Let's apply that recipe to 8 contiguous 24s from 10.10.32.0 all the way through 10.10.39.0. The first 2 octets are obviously identical, so the action is in the third octet. Write each one in binary, and you'll see the top 5 bits, 00100, never change, while only the bottom 3 bits cycle through every combination from 00 to 111. That's exactly 8 values, which is why 8 subnets collapse perfectly. Add it up. 8 bits plus 8 bits plus the 5 common bits gives a 21-bit prefix. So the supernet is 10.10.32.021. Now here's why we bother doing the math. Picture a branch office with three internal subnets: engineering, sales, and manufacturing, each A24. Without summarization, the branch router tells the ISP about all three, and the ISP installs three separate routes. With summarization, the branch advertises a single 10.1.0.022 that covers all three, and the ISP installs just one. Scale that across 1,000 branches, and you've cut 3,000 routes down to 1,000. Same reachability, a third of the table. But summarization raises an obvious question. If a router has multiple routes that all match the same destination, how does it pick one? The answer is longest prefix match. Say a packet is heading to 10.10.34.50. Four routes in the table technically match. The default, A8, a 21, and a 24. The router doesn't weigh them or average them. It simply picks the most specific one, the longest prefix. So the 24 to branch AMFG wins, because 24 matching bits beats 21, beats 8, beats 0. And that exact principle scales all the way up to the real internet. At the top, IANA holds the entire address space, 0/0. It hands large blocks like a 8 down to the 5 regional registries: Erin, Ripe, Apnik, Lacnic, and Afrinic. They carve those into smaller pieces for ISPs, who slice them again for big enterprises, and finally down to individual offices and hosting customers. Each layer summarizes everything beneath it, and that's the only reason the global BGP table stays around 1 million routes instead of billions. But summarization is powerful precisely because it's blunt, and that means it can break things in ways that are genuinely hard to debug. There are 5 classic traps. Summarizing non-contiguous subnets like 0.28, 30, and 31 while 29 is missing creates a black hole. Advertising a huge block like 10.2.0.0.8 sweeps in networks you don't actually own. Forgetting that prefixes must start on natural boundaries, miscounting bits. Remember, combining 4 subnets costs you 2 bits, not 4. And finally, trusting longest prefix match when a more specific route points the wrong way. Each one routes traffic into the void while your summary looks perfectly clean. So let's pull the whole lesson together. Worcester replaced the old class system by spelling out, with a single number after the slash, exactly how many bits belong to the network. Supernetting is just the reverse of subnetting, gluing adjacent blocks together at their common prefix length. That shorter prefix is what powers route summarization, which keeps routing tables small and lookups fast. And when multiple routes overlap, longest prefix match always wins. This more specific route beats the more general one every single time. And here's your cheat sheet. Everything from this lesson in one place to keep handy. Notice the 4-step supernetting workflow. Check that your subnets are contiguous. Drop the varying octets into binary. Count the leading bits they share, then pair that common prefix length with the lowest network address. And remember the shortcut. Combining n subnets shortens your prefix by log base 2 of n, so 4 subnets means 2 bits shorter. Screenshot this one. And that wraps up our deep dive into CIDR and supernetting. Next up in Lesson 22, we're shifting gears to private and reserved address space. The RFC 19.8 ranges you've probably already seen. A first look at how NAT lets those private addresses reach the public internet, and the special use blocks you'll want to recognize on site. If you're finding this series useful, head over to dargslan.com or the YouTube channel to keep going. I'll see you in the next lesson.